Okay, welcome back everyone. In this segment, we're going to be looking at friction and how we can use that when solving problems in Newton's laws. We're going to start with a couple of example problems, kind of continuing what we did last time. But what we want to get out of today's session is to think about what are the different types of frictional forces and what is their nature. And then how do we use Newton's second law to solve problems if we have one or more objects in a system? Okay, so here's our first example. We want to know how fast this block is going to be sliding at the bottom of the ramp. And so we're going to try to apply that problem-solving strategy that I talked about in the second video in this series. And remember that the first thing is to identify the object. In this case, it's the block. And the next step is to draw the forces, okay? So we are going to have the force of gravity, mg, going to have the normal force, Fn, and there's no friction, so we don't have to worry about that. We want to know how fast it'll be sliding, so eventually we're going for V final, which is going to be accomplished by getting acceleration. Okay, so we're going to get acceleration by solving F net equals ma, and we're going to do this in the parallel direction. So perpendicular and parallel. And F net parallel, this is our angle 20 degrees here. This is 20 degrees. So this means that mg sine 20 degrees is going to be equal to ma. Now notice that in this case you don't need the mass, and the acceleration is just going to be g sine 20. Which is about 3.35 meters per second squared. Now, in order to get the final speed, we can use the forgotten equation and say that V final squared is equal to V initial squared plus 2a delta d. V initial is 0, so 2, 3.35, and 12 meters. Multiply that out and take the square root, and we get V final is approximately 9 meters per second, give or take. Okay, we'll do another relatively simple problem. How high up this frictionless ramp will the block slide? And it turns out that in this case, it's going to be the exact same analysis of forces. When the block is on the ramp, we're going to have gravity going down. We'll have normal force going this way. So gravity gets split up into components, and the only force acting on gravity will be mg sine theta. So it will have an acceleration of negative g sine theta if we say that going up the ramp is the positive direction. Okay, so again, from the previous example, that'll be 3.35 meters per second squared, and this time we want V final to be 0. Okay, we have V initial is 12. So using the forgotten equation, V final squared equals V initial squared plus 2a delta d. We're trying to solve this for delta d. So delta d will just be, so V final is 0. It'll be essentially negative V naught squared over 2a. So that's good because that gets rid of our negative sign and acceleration. And if we plug and chug this out, we're going to get about 21-ish meters. Okay, so that's not too bad. Now let's take a look at a little bit trickier problem, okay? And we want to describe the acceleration of the 5 kilogram block. So when we say describe, we actually want to say calculate. Okay? The table and the pulley are magic and frictionless, and so we'll be adding in friction later on. Okay, so now we have a few more forces. We still have mg going downwards, which has its components, mg cosine theta and 20 degrees, and mg sine theta. And we have a normal force, but this time we have a tension pulling that back up. Okay, then we have a 1 kilogram block, which will have its mg going down and the same tension going back up. So this is important that these tensions are actually the same. Okay, and that's one thing that we say when we say that the magic pulley is frictionless. That allows us to say that these two tensions are equal. And in a later unit, we'll see why this is not the case. Okay, so we're going to apply Newton's second law, and we're going to end up having 3 equations. But first, we want to guess what's going to happen. And it seems reasonable to say that the 5 kilogram is going to go down the incline. So let's choose acceleration to be in this direction, down the incline for the 5 and upwards for the 1. We want to make sure to choose accelerations that are consistent. So for the 5 kilogram block, we're going to have basically F net perpendicular is equal to MA. F net parallel is equal to MA parallel. We're not even going to bother writing F net perpendicular because we're not going to need it. And for the 1 kilogram block, we're going to have F net in the y direction is equal to MAY. Now, this is different masses, so we could make note of that. And then we could just set this up as M5G sine 20 degrees minus T equals M5A parallel. Okay, so taking that gravity is 9.8, that would be basically 49 sine of 20 minus T is equal to 5A. Likewise, for the 1 kilogram block, we would have T minus 9.8, which is mg, right? 1 times 9.8 would equal 1 times ay, which is just a. Okay, so these accelerations have the same magnitude because the system is connected. The tensions have the same magnitude because it's the same strain. Okay? And so then we can go ahead and combine these two together by taking our T minus 9.8, rewriting it slightly, and adding those together. So we have a system where the tensions cancel out, and 49 sine of 20 minus 9.8 equals 6a, which is going to give us an A of approximately 1.16 meters per second squared. So it's not very large, but it is non-zero. And then we can go ahead and solve for the tension here by noting that the tension is A plus 9.8. Now remember that there's a 1 in front of that. Okay, so the tension will actually come out to be in newtons, and that's 9.8 newtons. Okay, so if you do basically 1.16 plus 9.8, you're going to get essentially 11 newtons of tension. And that's the same tension everywhere in the rope. Okay, so it's good that we were able to do some practice problems. Now let's just take a moment and talk about friction. So friction opposes sliding motion. Okay, it really opposes relative motion between two objects. Okay, and we have 2 types of friction. We have static friction, which occurs before sliding occurs. Okay, it's trying to get something moving. And then we have kinetic friction, which exists after sliding occurs. And you'll notice that static friction has a weirder math relationship. There's a less than or equal to sign. So imagine that you start out by pushing a very heavy desk with your pinky, and maybe you're applying 0.1 newtons of force. Well, in order for that desk to not accelerate, it's got to have 0.1 newtons of static friction to oppose your push. Okay? So in other words, the static friction will grow in response to the applied force until a certain amount. Okay, and that certain amount is mu times the normal force. So if we're going to sort of graph, okay, F applied versus F friction, there would be a linear relationship up into a certain point, and that point is where you get to mu s times the normal force. Then what happens is it drops down, and no matter how much applied force there is, you would have kinetic friction, which is a constant value. So in other words, static friction increases depending on the situation until you reach a maximum value. When you reach this maximum value, then kinetic friction takes over, and kinetic friction is less. You might think of this as it's easier to keep something moving than it is to start it going. Okay, so let's draw a free body diagram for a braking car. Okay, so if it's braking, it's going to be pretty simple. You have the car, you have gravity, you have the normal force, and the friction will be opposing its motion. So even though its velocity will be forward, the force of friction will be in the negative direction. Okay? And now let's draw a free body diagram for a car accelerating from rest. Again, we'll have mg and we'll have F normal, and these typically cancel out. But now friction will be pushing the car forward. Okay, so it's very important to recognize that friction doesn't always keep things from moving forward. Sometimes they actually push things forwards. Okay, so it can be a little bit complicated. All right, now what about for friction on a ramp? What does it look like if we're sliding down a ramp? Okay, so we're going to have kinetic friction. We're also going to have force of gravity, normal force, and then kinetic friction we usually draw as an Fk, and it is acting sort of at the corner of the object. It acts, the normal force acts between two objects at the point of contact, and so does friction, but it acts kind of at the bottom. And gravity acts at the middle. Okay, now what if something is sliding up a ramp? So again, we have gravity, we have normal force, and if it's sliding up the ramp, then friction will typically be pointing down the ramp. And this is kinetic friction in both cases. Now, another thing to point out is that friction is parallel to surfaces, which is what we're kind of showing in this example. So imagine that we have a 1 kilogram book that's being held against a wall by pressing it with a force of 50 newtons. What must be the minimum coefficient of friction between the book and the wall such that the book does not slide? So we're looking for mu s. Now if the book is not sliding, that tells us already that we have equilibrium, that the net force is 0. So this means that F net x must be equal to 0 and F net y is equal to 0. But before we go any further, let's go ahead and draw some of these other forces. Okay, so we're going to have, there we are, friction going up, normal force pushing out, and weight pushing down. So what we can say from this is that in the x direction, F minus n equals 0, so the applied force must equal the normal force. And in the y direction, friction minus the weight is equal to 0, so static friction minus mg is equal to 0, or static friction is equal to mg. But at the same time, static friction is less than or equal to, the force of static friction is less than or equal to mu times the normal force. So we have mu times the normal force is equal to mg. And we're also given that the normal force really doesn't like me today. We're given that the normal force is equal to the applied force, so mu s times F is equal to mg, and finally we can get that mu s is equal to mg over F, which is just going to be 1 kilogram times 9.8 over 50, which is a little bit less than 2. Okay, so the answer here is just about 0.2. Okay. Next example. Let's say we have a coefficient of static friction of 1 between the tires and the road. What's the length of time it would take for a car to accelerate from 0 to 60 miles per hour, which, if you convert it, is 26.8 meters per second. Okay, so here's our car. We have normal force, we have gravity, and we have static friction, which must push it in the positive direction. So that's the only force that must be equal to ma. Okay? And so what we can do here is we can plug in mu s F normal is equal to ma, and in this case the normal force is just equal to mg. So the acceleration is mu times 9.8, which is just 9.8. And once we have that, we know from kinematics that acceleration is change in velocity over change in time, which is v final minus v initial. V final is 26.8 meters per second. Delta t is what we want, and a is 9.8. From this, we can get that the time it takes is about 2.7 seconds. Okay, so we have one more example problem. So go ahead and try this real quick. So now we want to know how far would the car travel after the driver applies the brakes if it skids to a stop. So now we have mu kinetic is 0.80, mu static was 1.0, and now what the car is going to be doing is it'll have normal force, gravity, and kinetic friction, even though its velocity is in the positive direction. So how far would it travel? We're going for delta D, and we could find that by using the forgotten equation, v final squared minus v initial squared over 2a. So the intermediate we're looking for here is a, and we would solve this by noting that F net equals ma, and the only force in the x direction would be kinetic friction, and it would be in the negative direction. Okay, so this would be mu k times the normal force, which is mg. And so we get something similar, that a is equal to negative mu times g, and that's going to come out to be about negative 7.84 meters per second squared. We plop that into here. We note that v final is 0. V initial in the previous problem was 26.8 meters per second. We square that. We divide by 2 times negative 7.84 meters per second squared. And we're going to get that this distance to stop is about 45.8 meters. Okay, so that's a pretty good introduction to friction. We didn't do a whole lot of problems of friction on an inclined plane, but you'll see some examples of that as you work through the homework. So next time we're going to be looking at centripetal force.